So this is the setup that we have. We have a spring with a meter stick in the background to tell us the distance has been stretched. We have a motion detector underneath, which will be able to detect the distance to an object even while it's moving. And then our LabQuest will display that reading. You can already see that I've run it once and it has graph on it. I've already measured the spring constant to be 8.4 newtons per meter, and we can quickly estimate that because 8.4 newtons per meter means that if we stretch it 1 meter, it will take 8.4 newtons to do that. If we instead want to stretch it 1/10 of a meter, it should take 1/10 of the newtons, or 0.84. Well, I have a mass that's almost 0.84. So mass is different than a force, but the mass of this being 88 grams times gravity, which is about 10 meters per second squared, will give us about 0.88 newtons. So if we put this on the hook, we'll see that it stretches about 1/10 of a meter, or 10 centimeters. Even just estimating, you can see in the background the hook's about 66, and without the weight it's about 58. But like I said, this is not exactly 0.84 newtons. I'm estimating, so I've already done that check in the background. Now, in addition to what I said before, parallax error, or the angle at which the camera is pointing at the ruler, affects the measurement that we see. So if we look at the top of the hook, we see 65 now, but if I move the camera, then we see 67, or any value that I want to see, really. And that brings me to the point of just rest assured that the estimate is just an estimate, and I've taken the time to carefully measure it already. So, spring constant 8.4 newtons per meter. Now, next we want to show an undamped simple harmonic motion. And the way this motion detector works is by measuring sound waves, the time it takes for it to emit a click, bounce off the object, and come back. This time then can tell us the distance because we know the speed of sound. Now, it's not a perfect system because the click has to bounce off the object and not off other things in the room, and the speed of sound can vary with temperature, but overall it works. So when I click on record, the LabQuest is going to record the varying distance from the motion detector to the weight, and we will do that now. I will give it a random start. So we can see that an approximation of simple harmonic motion gives us a sine wave. Now, I've zoomed in on the graph the LabQuest made, and I'm going to highlight a couple sections to give us the values off of it. So we see the LabQuest has recorded position and velocity. It actually uses the derivative in order to get velocity from position. So it doesn't actually measure velocity directly. It does measure position directly based on the sound, well, rather the time that the sound takes to travel to and from. On the graph we can see the position here I have highlighted, and it's 0.176 meters, and I'm going to highlight the top as well, and we can see that's 0.256 meters. So the difference between those two would be the amplitude, and I'll pause the video and highlight the time. So the time it took to go one period is down here on the lower right, 1.65 seconds. Now the reason I said earlier that we were approximating simple harmonic motion was because in the real world everything does decay due to friction and air resistance and things like that. And so in reality, over a long period of time we can see that this is damped harmonic motion. But over a short period it approximates simple harmonic motion, non-damped. Now, as before, I'm going to give you the values. The time I've taken is 3 minutes across, and I've already zoomed in and recorded these positions. So up here it is 0.253 meters. Here it is 0.175 meters. Here 0.224 meters. And here 0.205 meters. So obviously the midpoint would be the center. The last important thing to show is that even though the amplitude is changing over the graph, the period will stay the same. So I'm going to zoom in and show the period of the beginning of the graph and the end of the graph. So I also have to make a correction. Earlier I looked at this box and thought that it was the period between two spots, but it actually only gives you the time of the highlighted section, or this circle, not the highlight here. In other words, not the difference, just the time there. So if I check the time here, it's 1.35. Here it's 2.15, and the difference will be the period. Approximately top is 177.5 and 178.3, and the difference between those two and the last two should be the same.